right, I feel the positive energy in the room, and that's a great thing. I apologize for interrupting you, but it's time to kick things off here. So, first of all, my name is Chris Hsu. I'm the head of Course 3, Department of Materials Science and Engineering. On behalf of myself and my department, welcome, and thank you for joining us today for the 2014 Fall John Wulff Lecture. So before we jump into the main event here, I want to give you a little bit of background. This is something that we do periodically in Course 3 every year, or sometimes every semester. We hold a John Wulff Lecture, and the purpose here is multifold. One of the purposes is to celebrate one of the legendary instructors that came out of Course 3, John Wulff, who you'll see here on this slide. John Wulff was a celebrated faculty member in Course 3. He had a very long and illustrious career. He was a professor in the department starting in 1937 until he retired in 1973. And he had an inspirational career not only in research, but what we remember of John Wulff is his legacy in teaching and mentorship and inspiration. An inspiration of young people to pursue with passion their studies in material science and engineering. He is famous for many educational contributions. Among those is his 1968 development of the course 3091, which I think meets in this room. Did anybody here take 3091? Show of hands. Is anybody presently taking 3091? Show of hands. Great. And did anybody TA for 3091? I see a handful of those people as well, right? So this is a course that has been active at MIT for a long time, has impacted thousands and thousands of people, and introduced them to the field of material science and engineering, and we're grateful for that legacy to Professor Wulff. He also, with some collaborators, wrote what is perceived to be a really groundbreaking set of textbooks that was called The Structure and Properties of Materials. And it was really singularly responsible for bringing students from other disciplines to look at material science and materials engineering as a possible career path. Because the truth is, in material science and engineering, what we do is we sort of use the tools of many other disciplines to build solid matter. So you can see the kind of adjectives that we're using to describe Professor Wulff. In fact, this is a picture of Professor Wulff lecturing in 3091. And I want you to notice the facial expression and the blurry photography here. We've also got photographers today, and I promise equally blurry photographs and equally vivid enunciation and emotion from today's speaker as well. So, it is really about inspiration, and it's about inspiring young people to think about material science as a career path. And in Course 3, we're pretty passionate about materials, that materials are not only worthy of study, but worthy of focused design, right? That's really what we do in this department. We are builders, we are engineers, but what we build is solid matter. And so some engineers sort of take components and put them together to make systems. They might make a macroscopic system like an engine if they were a mechanical engineer. They might put together circuit elements if they were an electrical engineer. If you are a materials scientist, a materials engineer, what you do is you sculpt with atoms. You put together atoms in exactly the right way to get the best possible potential out of a solid piece of matter. And because you're building solids, what you're really doing is making the ingredients out of which everything else on Earth will be made, right? So you're making the fundamental matter out of which all other engineering disciplines in the end will flow. So the revolutions that you've seen before your lifetime and during your lifetime, whether it was in lightweight materials that enabled flight, the materials that allow the communication and information revolution, or the coming suite of materials that harvest and store energy and help us maintain a green and sustainable planet, these are all at their heart enabled by engineering matter. And that's what we believe in and we're passionate about in this department. So, I don't know, it seems like we have a lot of young people. In fact, it's exclusively young people in this audience. I don't see a single person over 30, including myself. So, so that's good news. So I guess I would ask, are there any freshmen? Are there any people in the room who have sort of not committed to a discipline yet? So, this one's for you. We do this because, we're passionate about what we do. We hope today to share the passion of what we do and convince you that this is something interesting to think about. A lot of us got to this department because we loved physics, or we loved chemistry, or we loved biology. We loved the nerd stuff, but we also wanted to build. And I think that's the story that you're going to hear today from today's speaker. And today's speaker follows in a long line of excellent Wulff lecturers, and I like to put this one up first because this was the very first Wulff lecturer, that is John Wulff himself, who gave the first Wulff lecture in his own honor in 1977. That's got to feel good, right? And that brings me to today's speaker, who I am tremendously excited to introduce to you. A good friend, a colleague, Professor Jeff Grossman, is going to give us the lecture today. And for me, this is sort of personal because Jeff and I have been sort of in orbit around one another for our entire professional careers. So both of us had some of our training at the University of Illinois, Oski Wow, where actually, so Jeff was at Johns Hopkins University and then University of Illinois, and he got his training in physics. And so you're going to see a story of someone who really started in one field and saw the power of taking those skills and translating them to materials science. That's an important aspect here. And his interests in materials science and engineering are really about taking basic science and connecting to economics and sustainability and energy, and that's the theme of his lecture today. He is very famous world over for his research on those topics. He uses theory and simulation to understand the way we design and build materials, and he applies them to all kinds of applications. I think you'll hear about them today. I want to mention that one of them, if you go on the Smithsonian website and they rank the top achievements in science, I guess this is about 18 months ago now, they sort of listed their 5 top scientific breakthroughs. You know, there are things on there like incredible things like the discovery of the Higgs boson and so on. And on that list is Professor Grossman and his proposed desalination membranes that are just 1 atom thick. So I think you'll hear about that today. The other thing I want to mention about Professor Grossman is that he's not only a famous researcher, but he is the embodiment of what we think of when we think of John Wulff. He is that inspirational teacher. He's been involved in our undergraduate corps since he's been at MIT in 2009, and he was the chair of our undergraduate committee that helped sculpt the curriculum into what it is today, and he's a lecturer in our corps. And again, this is sort of personal for me because this semester I'm co-teaching with Professor Grossman, and I can assure you personally that his lectures are of the kind that you saw from John Wulff, with a lot of blurry motion and emotion, right? And so I think you're going to feel it today in your gut when Jeff is talking to you. And I also have learned from experience teaching with him that you don't want to sit in these first 3 rows. Because you probably will get wet and you may get set on fire. So if you guys want to change seats, this would sort of be the time to do that. At any rate, it is, without further ado, it's my great pleasure to introduce Professor Jeff Grossman to give the 2014 Wulff Lecture entitled, "Hey Adams, What Have You Done For Me Lately?"
Thank you. Thank you. Thanks. Thank you. Thank you. Thank you so much, Chris, for that incredible introduction. It's an incredible honor to have been asked to give this Wulff Lecture and to try to live up to the outstanding level of just inspiration and education that Professor Wulff set out to do. And so today what I want to tell you about, and I promise I won't light any of, well, you guys are my students, so, but I won't light anyone else on fire either. I want to tell you about energy. And I want to tell you about the way in which material science and engineering that Professor Hsu just described can impact the energy world. Okay? So to begin with, I want to start with the question, which is, what's the problem, right? Well, if we think about energy sort of historically, and you go back 1 million years, well, it turns out we didn't use that much per person. So I'm plotting here the energy per person per year in gigajoules. Most of it was just getting food. And then a little bit later, we started using tools. So we used a little bit more energy, right? And then after that, well, we started doing farming. We started using animals. And then we had advanced agriculture. And then, of course, the Industrial Revolution. And now we have this sort of ever-increasing thirst for technology, right? All of which requires energy. So there's this exponential growth in our energy consumption. And you may think, well, okay, so what? I mean, gas prices seem to be going down, right? What's the big deal? But you see, there are a bunch of problems with this. First of all, it's not fair. It's just not fair, okay? This is a map of the world scaled by energy consumption. So what you're seeing is that, for example, in the US, we're bloated, right? We have only 4% of the population of the world, but we use 20% of the world's energy. Whereas in other places like Africa, you've got 16% of the population of the world, but they only use 2% of the world's energy. Not fair. Right? Now, you may be thinking, well, okay, but eventually things will get fair, right? Well, so the problem is how that's going to happen, right? Because now, if you look at who's using energy more and more, so you look at the growth in energy consumption, you see in the US from 1990 to 2008, we had a 20% growth. But in places like Africa, it was 70%. In China, it was almost 150%. India, 90%. So these countries that don't have it, where it's not fair, they want it. And they're getting it, and they're going to get it in one way or another. Okay, so still you may be asking, why is this a problem, right? Why is this a problem? Well, the problem is the way we're getting our energy now and the way they're getting it now. And it's, of course, from lighting things on fire, right? It's from lighting fossil fuels on fire. Right? The problem with that is that there's only a finite amount, right? There's only a finite amount. So if we look at, for example, how much fossil fuels there are versus consumption, it's matched this tremendous growth really closely, really closely. And we've been able to match the demand with the supply, but because it's a finite resource, that can't continue. Right? And so what's going to happen, if you look at, say, a time frame out to 2150, is that the amount of this tremendous resource is going to start going down as we use exponentially more and more of it. And you can imagine that that's going to get us to a very important tipping point, right? The place in which we can no longer meet the demand. And we're using more and more and more quickly and needing more and more, but having less and less. And that's the peak of this fossil fuel sort of era. And it's debated about, are we before the peak, are we at the peak, are we after the peak? That's a really important question, as you can imagine, because of how it's going to impact the economics and the world in general. But I also like to take the longer view, which is if you zoom out of this by, say, 10,000 years or so, and you look at this, it's actually just a blip, right? It's really just a blip. And so, before the blip, we had muscle and firewood. What are we going to do after the blip? I think these are really important questions to ask ourselves. How are we going to supply the world's energy, both in the short term and in the long term? Now, I told you that we light stuff on fire, and actually, that's where we get almost all of our energy from today. And when I say things like light stuff on fire, it makes me want to light stuff on fire, which I like to do. And so I'm going to, of course, wear my safety goggles. And I'm going to light one of my favorite things to light on fire. Of course, it worked. Oh, I'm going to use this one, which is a candle. Now, you all call it a candle. I call it C25H52. And what we're doing here is I'm lighting this thing on fire, and it's going. It's a reaction that's happening. And what's happening is I'm getting energy out of this reaction in the form of heat. Right? So I'm breaking up this molecule, this carbonaceous molecule, and I'm getting 14,600 kilojoules of energy per mole of C25H52. Now, you can light other things on fire, and again, I really like doing this. So let's light propane on fire. Okay, don't worry about, turn it this way. Yeah, that's probably a good idea. So there's propane, and when I do that, I'm getting 2,874 kilojoules per mole of propane, right? So that's another way to get energy from lighting stuff on fire. And then there's my favorite. Now, you see, we could take the carbon out and just light hydrogen directly, right? And if we do that, how many of you want me to light hydrogen on fire? All right, let's do it. Let's do it. And now, if we do that, so you take, these are hydrogen bubbles, right? You get really cool amount of energy. That feels really good, right? Yeah. Now, let's do it again. Sorry, don't mind me. I actually could do this all day, as you can probably tell. But I have other things I want to share with you. But note, one thing that's interesting about this is the hydrogen reaction was actually less energy per mole, right? It was this tremendous flame. I may come back and light some more later. But for now, let's focus on why that's less. Well, it's because we're actually breaking bonds, right? So it's not just how many moles of these molecules you have, carbonaceous molecules for the most part, but it's how many bonds they have. And essentially, that's what we're doing, right? Here's another reaction. This is methane, and it's combusting. But what I want to illustrate here is that basically what you're doing is you're taking the bonds of this molecule and you're changing them. Now, those bonds were at some high level of energy, and they go down to a lower level, and the difference is what I get in the form of heat when I combust, right? Now, the interesting thing about this is that these are bonds that were made for us by nature over millions of years. And you can think about it like this. Nature pushed these materials up a hill. They pushed them up a hill. And it's the bond energy they pushed up a hill. And when I light it on fire, it rolls back down, right? So these materials were prepared over, 50, 100 million years or so by nature. And it pushed these energetic materials up in energy so that when I light them on fire, it rolls back down and I get that energy. Now, that's how we run our world. We light stuff on fire. And you do it all the time. You turn on your light switch, you're lighting something on fire, right? You are. You turn on your TV, you're lighting something on fire. It's just happening at a coal plant down the road. But you're still lighting stuff on fire. That's how we power our world, by letting go of these things that have been pushed up a hill by nature over millions of years. Now, it turns out nature's not the only one who knows how to push stuff up a hill for energy. We do too. And we do it pretty well, right? Like we can pump, this is pumped hydro, so we can pump water up a hill. So it's one of the easiest ways to store energy. And one of the only ways that can actually scale up to very large sizes. So we like pumping things up a hill. And then when you need the energy, you just let the water roll back down, right? It's a really great way to store energy at large scales. Not very efficient, but it works. Now, that's the water molecule. And so the question that I ask is, well, what else do we pump up a hill? What else can we pump up a hill and let roll back down? So there's a water molecule, but there's also atoms and electrons, right? Now, I love pumping electrons up hills and letting them roll back down. And in fact, I love it so much, and for safety reasons, I could not have hydrogen bubbles on your desks. But each of you should have a little bag. And in that, what you have are devices to pump electrons up a hill. And I'd like to do that now together, okay? So work with me here and take out this one here. This is the piezoelectric. It looks like this. And what I'd like you to do is put it on your desk and tap it. Just tap it. And see if you can see the LED. You may have to kind of go like this, but see if you can see the LED lighting up when you tap it. Okay? Don't get to the thermoelectric yet. That's next. This is the piezo. Do you see the light? Are you getting the light coming on? Okay. All right. Just tap that piezo. There you go, on the side that has the white disc on it. Okay. So what we're doing is we're converting energy from one form into another. You tapped, and you may have to put it down and tap it kind of hard, okay? You tapped this material. See, the key is the material inside. It's a piezoelectric, right? And the specialness of this is that in a piezoelectric, what happens is when you squeeze on the atoms, a dipole forms. So you get a little tiny field that's able to drive electrons where? Up a hill. Now, you tap it, you push the electrons up a hill, they roll back down, and I use that as work to make the light come on. You literally are pushing electrons up a hill with your finger. How cool is that, right? And it's all because of the material and its properties inside. Now take out the battery and thermoelectric. Don't connect it yet. Don't connect it yet. The battery is a way of storing energy. And it works with reactions. So what you have are different materials. You can just take copper and zinc, for example. And the reactions that happen between these materials carry charge, right? So now it's the chemistry that's pushing electrons. It's kind of like a limo driver for electrons. These atoms are like the limo driver, and they shuttle back and forth, and they carry them up the hill and down the hill. Right? It's a reaction. Now, what we're going to do with this reaction is we're going to create a temperature gradient. So what I'd like you to do, make sure you have your finger on each side of the thermoelectric, okay? And while you're holding both sides, close the loop by attaching the black wire to the copper plate. It might be on the battery, or it might be just freestanding. Oh, don't burn yourself. It can get hot. Okay? Now, what's happening here? what's happening is, again, I've pumped electrons up a hill, and it's the material. It's all in the material. I have, in this case, you have bismuth telluride inside that thermoelectric, okay? And bismuth telluride is special because when you have electrons going through it, they can carry heat, okay? But they can carry heat in different directions depending on which type of the bismuth telluride material you have. That's why you can create an energy gradient. You're not just heating, it's not just Joule heating, you're creating a hot side and a cold side, as you can feel, right? Okay, now, the last one is the solar cell. Now, I don't think there's enough energy from the room light to power those LEDs. There might be. Some of you might have a cell phone that has an LED on it. That seems to be enough. You could try it. But in any case, it's the same idea. Oh, and by the way, I want you to take this home. So it's okay if it doesn't work here. Take it home and put it next to a light bulb and show it off to your friends. These are party favors. I want you to take these home. You know what? Take them to the club, right? Take them to the bar. The freshmen are only going to alcohol-free bars though, right? Anyway, there's no better way to start a conversation than by saying, hey, you want to see me pump electrons up a hill? There's no better way. Trust me, I have tried it many times, all right? Take these home, play with them. That's what they're there for. The solar cell does work. You just need better light, okay? So these are your energy technologies. And the solar cell works, again, because of the specialness of the material inside. This is silicon, all right? Now, in silicon, the idea here is that I can take light, energy from the photons of the sun, and convert that into electricity. Why? Because that energy is what's my pump, pumping those electrons up the hill, and I let them roll down and do work for me. Okay, so charge is extracted in the same way, letting the electrons roll down. Now, you might be thinking, wait a second, I've stored and converted energy right here in my desk, right? And I didn't need to light anything on fire. Aren't we kind of like there? Like, this is cool. You're doing clean tech. There's no fire. It's all like beautiful. But there are problems, right? And there are challenges. And here's the thing. If we look at these materials first, from the point of view of their cost and efficiency, you could charge your cell phone with this piezoelectric. You could. If you tap it every second for 208 days, okay? Now, at MIT, we like to do these calculations first and then sort of think about whether we want to engage it. But if you see someone doing this, charging their cell phone this way at a cafe, it's probably a Harvard student, just go help them out. Just explain it to them kindly and talk to them about electrons and hills and all that. See, if you wanted to power the US electricity with the battery, it would cost you $25 trillion, okay? And not only that, but the battery would only last for 1,000 charge cycles. And if it were based on, say, lead acid, which is the cheap stuff that's in your car, well, there's not enough lead. We'd need 50 times more lead than exists in the world, right? So with batteries, we have challenges as well. Solar cells cost 3 to 5 times more per electricity than compared to coal or natural gas, so they're not competitive yet. And plus, you only get electricity when the sun's out. That's a challenge. And with thermoelectrics, if you had boiling water on one side of it and ice cubes on the other side, so you can drive it in reverse. You can either create a temperature gradient or you can use a temperature gradient to create electricity. If you did that for 12 hours, you could charge your cell phone. But that's a lot of heat and cold. And by the way, 98.5% of it would be completely wasted because these are not efficient materials yet. So this is the problem, right? These materials are beautiful. And these technologies are beautiful in what they do, but they're not good enough yet. Okay? Now, what do we do in material science and engineering? As Professor Xu said, what we do is we talk these materials at the scale of the atom. We go down to the scale of the atom and we say, what are you doing down there? And how do you work? And what can I do better? So let's look at these materials at the scale of the atom. If you do that, and you look at, say, these are in milli-electron volts, how much energy you could convert or store for each atom inside the material, what you would see is that the numbers are pretty low. It looks good for the battery, right? 0.4 millieV per atom. The piezo that's not good. The thermoelectric is 0.001. But here's the problem. Here's the problem. Okay, this I want to light it again, but But that one is 1,900 millieV per atom, right? So this is the thing. The fossil fuels blow away the competition. And that's the thing. Every atom, but nature had millions of years to do it for us, but every atom participates in a way that's incredible, right? In terms of the energy you get out of each and every atom in those materials, it's a beautiful thing. Almost 2 electron volts for every atom that you burn, right? And that's what we need to do as material scientists and engineers for these other clean technologies. That's what we need to do. And so what I do is I ask these technologies this question. I say, hey, yo, atoms, what are you doing? What have you done for me lately? And what are you going to do in the future, right? And how can we do better? I ask every single one of them. Sit up, sit straight, eat your spinach, do your pull-ups, do something better than you're doing now. And so that's the question that we ask continuously as we try to design better energy technologies. And actually, because it's so important that these atoms hear you, I want you to help me. I'm going to ask this question a couple more times, and I want you guys to help. So I want to try something out. I'm going to say, hey, atoms. And I want you guys to say, what have you done for me lately? And you don't have to sing it the way Janet Jackson did. Some of you may know what that means. But I would like, I would like you to say it. So I want to try that out, okay? Because we're going to do this a couple times. So I want to really wake these atoms up. Ready? Hey, atoms. What have you done for me lately? That was pretty good. That was pretty good. But I want like building 1 to hear us, okay? Are you ready? Hey, atoms. What have you done for me lately? Now we're talking. Okay. But I still think President Rife in the Great House needs to get a wake-up call from us, right? Let's do it. Ready? Hey, atoms. What have you done for me lately? That's it. That's what we do in material science and engineering. We ask that question, and that's exactly, in our faculty meetings, that's how we roll all the time. We're constantly doing that kind of back and forth. You can ask Professor Shu. So what I'm going to do now, I'm going to ask this question, and I'm going to ask it in 3 examples of things we're doing in my research group, okay? And the first is going to be solar cells, then it's solar fuels, and then I'm going to talk about water, which is also an energy problem, okay? And these will just be examples of how we ask this question and what we can do about it. Now, to motivate solar cell research, I just have one very simple slide. All of the coal, oil, and gas in the world known to humans, that's everything we've dug up and burned and everything we could possibly dig up and burn, is the same amount of energy that you get from the sun in 20 days, okay? I think that pretty much is enough to motivate why this is such a great resource for us. Now, but again, we got to go down to the scale of the atoms and understand this material. So what is a solar cell doing? Well, when you have this piece of silicon, which I mentioned is what this is made of, when you shine light on it, what's actually happening is there are electrons in that material, okay? And those electrons, when a photon comes in and it hits an electron, it actually bumps it up. The photon energy goes to the electron, and that pushes it up a hill. It really just pushes it up a hill. And so that electron is literally pumped up. It's like how we get pumped up for things, right? I get pumped up to watch the Celtics. I don't know why anymore. But, this electron is totally pumped up. It's pumped up to go and turn on your light. It's pumped up to go and send your text message. It's pumped up to Snapchat, even. That electron is ready to go. And all you need to do, see, it left behind a positive charge. It's a negative charge that leaves behind a positive charge. All you need to do is then get them out on opposite sides, and that's exactly what this solar cell is doing, okay? The sun is your pump. But as we talked about, there are limitations, there are challenges. We need to ask these atoms a question. Hey, atoms. What have you done for me lately? All right. Let's ask that of the solar cell. And the first thing I'm going to ask is, how good of a pump are you? Almost all solar cells you buy today, including the ones you have in your hands, are made out of silicon. Well, it turns out if you look at how much silicon can absorb light and convert it into current, which is what I'm plotting here, as a function of the thickness, it's really bad, right? It's really bad. At a micron thick device, you're only getting about 7% or so of the sun's energy. Those are terrible pumps, right? Those are terrible pumps of taking light and pumping electrons. But if you look at carbon, it's much better. So if you take carbon, you look at how well it pumps, it's much easier for a photon coming from the sun to pump electrons from carbon up than it is silicon, right? Now, that's actually a materials difference. We literally changed the material. We went from a silicon atom just up in the periodic table to a carbon atom, and all of a sudden, the property changes, right? That's the role of the material. And those carbon atoms are like, hey, I listened, look at silicon. I'm like 10 times better, right? That's pretty cool. But see, you can also change the properties by structuring. Not just the material you choose, but in material science and engineering, we structure materials to change their properties. Let me give you an example, right? These are layered materials, molybdenum disulfide on the left and graphite on the right, now known as multi-layer graphene, but it's still just graphite. The thing is, so here's the interesting thing about these. If you take a single layer of this out of its stack, it's a 10 times better pump or more of electrons up from photons. That's incredible, right? And it has to do with effects that happen when you structure materials at the nanoscale. It has to do with effects that happen when you take these things and make them and control them at the nanoscale. So you get a factor of 10 or more just by taking the same material out of its bulk, right? You're not changing anything but the structure. And so what we did in our group is we asked the question, we said, well, how good could you make a solar cell using this better pump, right? Well, it turns out that if you look at a solar cell and you think about it in terms of how many atoms are participating, right? An important metric would be the power density. So it's how many kilowatts per kilogram of power can you make? That's really our per atom metric, right? Hey, atoms, what are you doing? Silicon is terrible. So if you make a 35,000 nanometer or 35 micron thick cell, it's going to be about 20% efficient. It's the best power density you can ever get out of silicon at that thickness. And it's 2.5 kilowatts per kilogram. If you compare it with the two-layer cell, because the pump is so much better, and it can take a photon and so much more easily give us electrons up a hill, you can get power densities that are over 1,000 times higher, right? That's pretty much near the limit that you can possibly do. It's really getting those atoms to shape up. It's getting them to really shape up and be like, okay, I'm here. I'm not silicon, that's laughable, but I'm not even carbon, I'm much better. I'm about as good as I can ever do, right? And that's what we want out of our materials. That's what we want to do, right? You can't beat this. I mean, you run this for a few months and you basically have the densities that are in reactor-grade uranium, right? So this is pretty much as good as you can do. Now, the thing is, though, when I ask the atoms to do the best they can, I want them to do the best they can in terms of properties, and I've been talking about the pump, but I also want them to do the best they can in terms of cost, right? So it's like, hey, do the best you can, and by the way, do it really cheaply, please, right? And so if you look at this question of cost for solar cells, this is one way to look at it. You have sort of the complexity of the material going from left to right, but what you have is on the left, you have very simple materials, right? You have silicon, more than 80% of all solar cells today made out of silicon. And it's a very simple material. It's the same atom repeated everywhere. That's easy, but not really, because you have to spend a lot of time and energy and cost to make this material. You have to go to high temperatures. As you go to more and more complex materials, though, which all of these are used today in solar cells, all of these can make that pump happen, right? But as you increase the complexity, the cost can go down. So you can make more complex materials, make solar energy a possibility, but they're much, much easier to make. You can make these in solution. You can make these at lower temperatures, right? And so the question we ask of these atoms is, well, how far can we go in cost? What have you done for me lately in cost? And it turns out, I told you about carbon being a great absorber of light. Well, and we've made solar cells out of carbon, but how cheaply can we make those? It turns out we have this wonderful source of carbon. The only problem is we just keep lighting it on fire, right? It's there. And it turns out that this is really cheap. We make 250 megatons of coal every year, 6 cents a kilogram, okay? Solar grade silicon is close to $1,000, right? It's many hundreds of dollars a kilogram. So, but the key is that if you look inside, these are really important and interesting materials. They're chemically diverse, and they might actually be more useful to us if we don't light them on fire, right? And that's actually something that we're looking at in my group. So if you take, for example, coal from Kentucky and coal from Virginia, and you shine X-rays on it, and you measure the electrons that come off, you can get a sense of some differences between these two kinds of coal. So you see, these coals have these carbonaceous materials in them, and they're different. Nature's already done work for us to make them different. That's exactly the kind of difference we try really hard to make ourselves. But nature has done it. And here we are, lighting it all on fire, right? But I claim that this kind of difference can be understood. And in fact, we know, for example, that if you have more mature coal, you're going to have more sp2-like carbon. That's just how the bonds are arranged. And that difference is something we can take advantage of and make devices out of. It's exactly the kind of thing we want. So what we're doing is we're actually using coal as our base material, and we're ball milling it and making devices. And we made sort of the first ever, so far, transistor out of coal nanoparticles. And I'm very excited about where this can go and the types of devices that you can make out of this material, maybe offering an alternative energy technology and market to the fossil fuels that we just light on fire today. Okay? So now we come to another example from the research we do, and this is another way of using the sun, but in this case, what we're doing is we're using the sun to make heat. Okay? It turns out, actually, so that's the simplest way, one of the easiest ways you could possibly use the sun. Paint a barrel black, fill it with water, and put it on your rooftop. Right? It's actually a tremendously well-used technology worldwide, just not in this country. It's the #2 most utilized renewable resource in the world, second only to wind. Okay? This country is number 17, in case you're wondering. But the problem is, whether you do it this way or whether you have concentrators and go up to higher temperatures, try to generate electricity, no matter what, the challenge with using the sun's energy this way is that you can't hold on to it. So as soon as you create heat, it re-radiates out. And that means that you have to use the energy in this way right where you get it. You can't store it, and you can't transport it. Right? But there's a way around that. There's actually a way around that. And these are called solar chemical or solar thermal fuels. These are molecules where when you shine light on them, they go through some kind of twist. They go through a structural change. Right? And they stay in that structural change until you want them to give back that energy in the form of heat. And then you trigger it, and it goes back and gives you the heat, and it's ready to be charged up again by the sun. This is actually not a new idea. This was heavily explored as an energy technology in the 1970s. But the problem is, with all the technologies that were looked at back then, it couldn't cycle. So you do this cycle, 10 times, and then you'd have half the material left, right? Because it would degrade. It's like if you buy a rechargeable battery, it only charges 10 times. That's not very useful. Certainly economically not going to work. So again, we go to these guys and these atoms and these materials, and we ask the question, hey, solar fuel atoms. What have you done for me? All right, thank you. I feel like we got to get back to President Reif levels, though. On the next one, we're going to. So we asked that question of these atoms in this material for this technology. And what we realized, we have to go back and we have to realize something. We have to realize that there are many molecules that switch. There are many, many molecules that are photoactive. They go through some kind of switch. The problem is they're just terrible energy materials. So the question we ask these atoms is, can you become good ones, right? Can you do more for us than you're doing right now? Because it ain't good enough. And to understand how to do that, we put on our materials design caps, we have to go back to our energy hill. We have to go back to our energy hill. And in this case, what you have is a reaction, right? You have a reaction coordinate, and you have energy. And you have these molecules that are uncharged, and then they get charged, right? And so they look like this in a reaction coordinate. And the difference between those two minima would be how much heat you can store. And then the barrier is what you have to overcome, both to charge it as well as it's sort of related to the stability in the charged state, right? So if we look at this now and we think about our molecules, let's take azobenzene. This is the one I showed you before. And what we do is we shine light on it. So now we have a photon coming in from the sun, just like in the solar cell. An electron gets bumped up in energy. But now, instead of taking it out and making it do work, like light up a light or something, now what I'm doing is, with that electron up in energy, I'm using it to get over this barrier here, okay? And it stores then the energy in the form of heat. Now, the thing is that what we want to do is increase the energy stored, and we want to keep that barrier high. Otherwise, the molecule doesn't stay in the stored state. So what we realize is that we don't have enough phase space here. So we sort of ran out of real estate of ways to push and pull on the molecule. But that changes if you put the molecule on a rigid template. So what's happening here now is if I put the molecule on a template, it's in a different phase. It's in a totally different phase than if it were in the gas or liquid or solid state. Right? So this is what it would look like on the template. This is just an animation, because animations are cool, where it's switching, but it's on a template and it's packed in. And the important part is, if you zoom in on this, what you see, this is a side view now, what you see is that those molecules are packed together in a way they would never exist otherwise. So we made like a new phase of this material, and because we made a new phase of the material, we can actually do different chemistry that wasn't accessible before, okay? And that's what we've done, and what we've shown is that this is actually a very broad phase space. You can take many different templates, and you can put many different switches on them, and you can boost the energy density tremendously, as well as the energy storage, right? So for example, with azobenzene, the one I've been showing you, you got 90 watt-hours per liter in the powder form, but you put these on nanotubes, and you get up to 690 watt-hours per liter, right? Again, I'm going into the atoms, and I'm asking them to do more by designing them into new materials. Okay? And that's actually now comparable to the best lithium-ion batteries can do. And of course, this is not electricity. This is heat. So you have to think about where do you need heat? It turns out there are a lot of places you need heat. For example, cooking, right? And some of you may know that wood-fired cooking, the toxins that come from wood-fired cooking in the third world is responsible for more deaths than malaria and AIDS combined, right? So it's a serious problem. Now, there are ways to cook with the sun, and I like that. That's a restaurant in India. Those are 2 solar cookers. And the reason I like these is that they come with specialized goggles and gloves. And you can see why. Because he's in his oven. He's in the oven. That's not very comfortable, right? But apart from comfort, the problem is you also can't cook at night. And so with this type of fuel, what you can do is, and this is together with Alex Slocum, is we've designed these cookers where you can charge them by flowing them past a glass plate, right? From 1 liter down into another liter, just use gravity to do the flow. And then when you want to cook, you flip it over, you've got a stainless steel top, and with 5 hours of charge, you can get about an hour of 300 Celsius hot plate, depending on what you do with that energy, of course. So that's one example of how we can use these types of solar fuel materials. It's a really interesting material if you think about it. The same molecule is converting and storing the sun's energy. That's pretty cool. Okay, in the last example from some of the work we're doing, I want to talk about water. Now, water is an energy problem. Water is an energy problem. In the year 2050, when we have 9 billion people, 4 billion of those people will not have regular access to clean drinking water. 4 billion out of 9. Now, a lot of the water that we have in the world, almost all of it, is in the oceans, right? It's just that we can't drink it because it's got too much salt in it. So we can take that salt out through desalination. And the best way to do that today, the most efficient way, is through something called reverse osmosis. This is a plant, this is one of the largest desalination plants in Israel. There are 40,000 of those membranes, and they're pushing seawater through. But here's the thing. It takes a 6 megawatt power plant to do that in the back. It's in the plant. Right? So half of the cost of doing this is still way too expensive to be something we can do all over the world. And half of the cost is in the energy. It's just in the energy of pumping the water through the membrane. So there's been a lot of advances in desalination, but not on the material that matters most, that membrane, that piece of membrane that you're pushing the water through. So we went to those membranes, and we asked the question. We asked, hey membrane atoms.
What have you done for me?
Oh, come on, let's try that one more time. Hey, membrane atoms. What have you done for me lately? I love it. All right. That was great. And here's the problem, right? The problem with membrane atoms is that they're very inefficient, and it's the same technology we used in the 1970s. It's the same membrane. These are polyamide active layers. That's what I'm pushing the water through, sitting on top of a polysulfone support layer. And these are very prone to fouling. Stuff grows on them. And then you use chlorine to treat it, just like we do in our drinking water. There's chlorine in it. And it eats away at the membrane. Not to mention the fact that it's very energy intensive. Right? So these are not the best materials. Right? So after asking this question, we thought about this. And we thought about, well, let's go back to our energy hill. Let's go back to our energy hill. Right? Well, it turns out in this case, when you push water through polyamide, it's got to diffuse all around, losing energy along the way, which you don't want, right? So here you have all these viscous losses as you're pushing the water through. That's where a lot of the energy goes. And if you think about it, how would you then tell these atoms to do better? How do you get them to do a better job? Well, you take a lot of them away. So you take away the viscous losses, and you make each one count. And the limit of a membrane will be a single atom thick. And that would be something like graphene there, where now when you push water through it, there's very little loss because of this diffusion around, right? And so what we did is we first did simulations where we pushed the salt water on the right, and we pushed it in a computer through a graphene membrane with a hole in it. And what we saw is that actually water comes out. Okay, that's good. And also, if you zoom in, there's a salt ion right there in green. You can see that it's coming right up to the pore, and it's getting rejected. But the water is going through. So these types of membranes can be highly selective, and we think they can be very high performers. So that's the next question we have to ask is, how well do they do? How much more water can we push through? And the metric that's used for that is called permeability. So if you look at the permeability of these membranes, and that's the liters that you can push through per area of membrane per day per pressure applied. Right? That's a log scale on the horizontal axis. And then the salt rejection is on the y-axis because they got to reject salt or it's not very useful. Now, if you look at the best performing membranes today in reverse osmosis, they're around 0.1 in their permeability. But if we use the ultimate membrane, if we get every atom to do the best it possibly can, then we have the single atom thick membrane, and the permeability goes up by a factor of 100 to 500, right? So this is very exciting because we think this is about the ultimate limit of how well atoms can do for you in filtration. Now, of course, thermodynamics will dictate the ultimate energy limit, but what we found is that with this increase in permeability, we can reduce the energy consumption by at least a factor of 2. Okay? So with that, I wanted just a few closing comments. You have this goodie bag, right? And you have all these great materials that convert energy and store energy in different forms, from one form to another. And I really want you to share it. You know, take it home, share it with your friends, and talk about pumping things up hills and show it off. But also, I want you to think about something, which is that what's limiting all of these things, the reason why we had to keep asking that question and wake up President Reif, well, not wake up, but, disturb. Is this being videotaped? Anyway, is that the reason we had to keep asking that is that it's a materials problem. The conversion and storage of energy is limited by the choice of material. It's primarily limited by the choice of material. Now, what gets me really excited about that challenge is that we live in a different age than ever before, right? Now, we tend to name the age we live in, sometimes at least, by the material that sort of dominates the technology of that age. What I love about living in today's age is that we can't do that anymore. We can't. Why? Because there are just so many ways in which we now know how to design materials. And we really, truly can put atoms where we want. And so I feel like we now live in this sort of materials design age that opens up all sorts of possibilities, and it's exactly what's needed to solve the energy problems and to make these technologies that you're going to take home more and more efficient and less costly. So with that, I'd like to thank some people. First of all, I'd like to thank the people who support this work, shown down at the bottom. But very importantly, I want to thank the people who do all of the work. And that's my research group. You may have noticed people wearing green T-shirts. And so that's got this on it. And that, thanks to Jenny Zhang for designing that, and that's pretty awesome. And thanks to my research group for being just so amazing. I actually feel, by the way, they're the ones who helped. We were an army that put together your goodie bags. That was fun. Talk about soldering 2,500 wires. It's fun. It's like a party. I recommend it. I recommend it. It's really fun. It's a good way to bond. But this is just, I feel actually really honored to have the chance to work with these people. These are amazing students, and I just feel really lucky to have them in my group. And they have these green T-shirts on, not just for the fashion statement, which it makes, but also because they want to talk to you, okay? So they're ready to talk about energy. They want to talk with you, not in like a weird, but they just want to, they're like out there, so come and talk to them and ask them questions. There's going to be this great food, and grab a green T-shirt. And they're like, talk about energy and pushing electrons up a hill, and they're like going to be there all night with you. They want to talk about it. So please grab a green T-shirt. Finally, because they happen to be here, I have to thank the 4 most important treasures in my life who are sitting right there, my 3 kids and my wife. And then last, I want to thank all of you for listening to me and for your attention, and thank you very much. Thanks. Thank you. Thanks, Chris. All right. Thank you.
All right, what did I promise you? I promised emotion and blurry photography and pyrotechnics, and you got them all. So that was fantastic.
We could light bubbles on fire. We could light more. Do it? Yeah. Bubbles on fire. Okay.
All right. Well, while he's lighting things on fire, we can also put him to work. If there are questions at this point, it would be our pleasure to have a few of those right now.
So cool.
And I'll give preference to those of you who self-identify as freshmen. So if you want to do that and ask a question boldly, please, now's the time.
Yeah. Do we need a mic there? Or,
So the carbon-based solar panels you were talking about, is there less pushback from like the coal industry on those?
Well, I'd love to get to the point. We're going to get to the point where we know the answer to that question because we don't have a working solar cell yet. But we have transistors, and we're building devices. Don't put any pressure, no pressure, but you could talk to him about it, for example, who's supposed to have a solar cell by the MRS meeting, working. No pressure, Brent. But it's a really good question, right? I mean, what I'd love to do is to show the world that these are actually interesting materials in their own right, and they may be useful for other energy technologies or other markets. And all we do is light them on fire. So I don't know yet the answer to your question, but I hope to find out soon. Yeah.
Go ahead.
Yeah.
So how do you actually manipulate and move around these atoms?
How do we manipulate and move around these atoms? That is a fantastic question. In the computer, it's fairly straightforward. we just change the XYZ coordinate in a file, right? But this really gets to the heart of one of the biggest bottlenecks in materials design, which is synthesis, right? So we know pretty much, we know a lot about how materials will behave when we make them or if we make them, but then can we make them, right? And there's no one answer to that question, but there are many answers that we have now at our disposal whether it's from very advanced fabrication facilities that can get down to patterning things at the scale of a nanometer, or whether it's from chemistries that we've learned how to do in a controlled way to grow things, right? To grow like crystals of quantum dots in solution, and then stop them exactly where we want, when they're 2 nanometers, for example. But it's a very important part of the problem, and it's one that I think there's still a lot of good work that needs to be done. Yeah.
Any other questions? Don't be shy.
Maybe up there.
One way and back, and then we'll come down here. Yeah.
Okay.
So state-of-the-art graphene is pretty small right now. Can you project when it will actually be possible to make these membranes?
Well, we're actually already making them. Where's Shreya? Oh, there she is. You can talk to her, no pressure. That was actually also a pun. So she's actually made membranes with graphene. Now, they don't work yet. So what we need to keep in mind when we do this is cost, right? So we don't want to make membranes out of a single sheet of graphene that we had to make with, say, CVD, which is very expensive to go to large scales. So what we're doing is actually making membranes from solution-based graphene that you make in solution, which is very cheap. I say they don't work, but there already are interesting properties about them. Like, for example, they look to be a lot more chlorine resistant, which is a very important part of the equation. But there's a lot of work to still do in terms of understanding how these pieces of graphene that we're putting down overlap and what's happening at those edges. And importantly, no one has drilled 1 nanometer holes across a membrane controllably before. So that's a pretty tough challenge, and we're trying to meet it.
Good. There was one down here.
Yeah.
So I think this all sounds exciting. So if I want to say,
Well, you were part of the research, so I hope so, Sam.
if I'm interested in getting involved, if I'm interested in getting involved and learning more, what sort of steps can I take beyond talking to people in this room?
I love that. That was a perfect. Thank you very much. Well, first of all, grab a green T-shirt. Grab some good food, which there is. Grab a green T-shirt and come talk to us. We love talking to you. I love it, and all my colleagues love it, and I love that my colleagues love it. Like in course 3, it might be true elsewhere, but in course 3 I know, we love talking to students all the time. So come talk to us. Send us an email. We'll actually write back. We will. And come and chat about and ask questions, and we want to actually talk to you about material science, no matter what department you're in. Want to talk to you about the things we work on or the things you're interested in. I think that's the best way, is just send us an email.
And I think we'll end on that softball right there. So,
Okay.
So as Professor Grossman has already indicated, there is an elaborate party set up outside this room. So please do hang around, talk to the green shirts and the faculty. And if you will please, before you run off, join me in another round of applause for Professor Grossman.
Thank you. All right.